Okay, we're going to talk about the ionic product of water, Kw. Well, we come across Kc. You probably come across Kp as well by now. And so you can tell from this that this is another equilibrium constant. Okay, and the reaction we're looking at is this. Okay, so we get two molecules of water, H2O, another one, a red one, and okay, you will form one molecule, right, one. So the black one is going to pick up a proton at the expense of the red one. Okay, so we form an OH minus ion and an H3O plus ion. Now that's, if you think about acid conjugate base pairs, then the black one here is behaving as a base. So that's call that base one. And when it's going backwards, this black one, the H3O plus, is behaving as an acid. So we'll call that acid one. The red H2O here is behaving as an acid because it gives away a proton to the other one. So we'll call it acid 2. And this one here is acting as a base when it's going backwards. Now this equilibrium is way over to the left. It's really far over to the left. So when you have any aqueous solution in front of you, nearly all of it is covalent H2O molecules, and a tiny proportion of it will be H3O plus ions and OH minus ions. Now, usually when we write this equation, it's usually people sort of simplify it and they say, right, H2O goes to H plus and OH minus, but of course we know H plus doesn't really exist, but that's just shorthand. Okay, so if you wrote down an equilibrium constant for this, Kc, we would write down Kc is equal to the concentration of H plus over OH minus divided by the concentration of water. Now the concentration of pure water is really, really high, okay? It is, the concentration, if you have a water, you work it out, it's actually 55.5 recurring moles per decimeter cubed, which is very high. How do we say that? Well, we've got in 1 dm cubed of water, we have got 1,000 grams. What's the moles of water in 1,000 grams? Moles is equal to 1,000 over the mR of water, which is 18, and that's equal to 55. Yeah, okay, so that's where that comes from. The main thing is that it's enormous, right? And the concentration, because it's so big, the concentration of these are really going to be small, like 0.1 mole per decimeter cubed and so on. So this is at least 500 times bigger. So for all intents and purposes, the concentration of water remains constant, okay? That's a constant. Now there's no point having two constants in an equation. So if we have, so what we write down is, right, Kc H multiplied by H2O. Okay, and we replace those two constants with one constant, which we call Kw. And so Kw, put it in blue, Kw is equal to the concentration of H plus ions, don't forget that's really H3O, and multiplied by the concentration of OH minus ion. Now that's all that other stuff I've just written above there. Forget about that if you want to, but don't forget that in the red box. That's really important. Now the value of Kw at 298 Kelvin, it does change a little bit if the temperature changes, but 298 Kelvin, which is 25 degrees C standard temperature, the value of that is 1.0 times 10 to the minus 14. Now we look at the units. The units, we've got two lots of concentration, so strictly speaking, the units are mole squared dm to the minus 6. That's what the units of Kw at, so that's pretty important as well. Okay, so let's remember all of that stuff. That is really important. The other stuff was a bit of just explaining what's going on. So what does that mean then? If we've got any solution you've got in front of you, so you may have a glass of water, you know, you've water, or you might have a beaker of HCl, concentration 0.1 mole per decimeter cubed, or you might have, some sodium hydroxide solution. Let's say that's 0.1 mole per decimeter cubed. In any of those solutions, we know if you multiply the concentration of the H plus ions by the concentration of the OH minus ions, it's equal to 1 times 10 to the minus 14. Okay. So what does that mean then? Right. Let's have a think about the acid first of all. So if you've got hydrochloric acid and you dissolve that in water, we know hydrochloric acid from GCS, we know it's a strong acid, so all of it will dissociate. So in other words, all of it will turn into H plus, which of course H3O plus, and Cl minus ions. So if the concentration of this is 0.1 mole per decimeter cubed, then the concentration of H plus is also 0.1 mole per decimeter cubed. Now, from the previous lesson, hopefully you remember that pH is equal to minus log to the base 10 of the hydrogen ion concentration. Right. So what is the pH of this solution? pH of this solution, so pH is going to be of this is pH is equal to minus log to the base 10 of hydrogen ion concentration is 0.1. Okay, so you put that into your calculator. The log of 0.1 is minus 1, so the minus log of it is 1. So the pH of that is 1. But what else can we say? Right, we know because these hydrogen ions concentration, because that is 0.1, and we know that that multiplied by OH minus equal to 1 times 10 to the minus 14. Well, let's work out the OH minus concentration there in that solution of acid. OH minus concentration is going to be equal to Kw over the H plus concentration. That's equal to 1 times 10 to the minus 14 divided by 0.1, which is equal to 1 times 10 to the minus 13 moles per decimeter cubed. Okay, so that may be a little bit surprising to you. You know OH minus ions make solutions alkaline, don't they? We did that at GCSE. And even in an acid solution, you have some OH minus ions floating around, but how much have we got? We've got tiny amounts of it. So you can see from this, the expression, when you've got high H plus concentration, the OH minus concentration must be tiny. Let's think about if we have a solution of sodium hydroxide now. Okay, so I'll do this sideways, I think. Okay, so we've got NaOH, concentration is 0.1 mole per decimeter cubed. Right, now OH is sodium hydroxide is very, very soluble. So the concentration of the NaOH is that, then the OH minus concentration in that solution is equal to the same, 0.1, because it all dissolves really well. So if we've got a high OH minus concentration, we know from the expression, that because the Kw is a constant, we know if OH minus is high, H plus concentration must be really low. So let's work out H plus concentration in that solution. H plus is equal to Kw over OH minus concentration. 1 times 10 to the minus 14 divided by 0.1. That's going to be equal to 1 times 10 to the minus 13. So what's the pH of that solution? Using this green equation here again, yeah. So pH is equal to the minus log of the hydrogen ion concentration. So that's equal to the minus log of 10 to the minus 13. Put that into your calculator if you like, and you will find that is equal to pH 13. And we know from that, pH 13, we know is a pretty alkaline pH. But even though in that fairly strongly alkaline solution, have we got some H plus ions? we've got some of them, but we've got a very low concentration of them. So you can see with this expression, really, when H plus goes up, OH minus goes down, and vice versa. So what I've done here is a little table. I'll look at those graphs in a minute, but we'll just look at the table here first of all. Oops. Right, so we'll see all that all together. Right, okay, so we can see here we've got in the black column H plus concentration and OH minus concentration. When you've got a high concentration of H plus, such in a solution of hydrochloric acid, we can see the concentration of OH minus is absolutely tiny. Yeah, and you may be surprised to see that you've got a pH of 0. Yeah, if you take the minus log of 1, well, the log of 1 is 0, so the minus log of that is 0. So you always thought before you can't have a pH of less than 1. Well, you can have one lower than that. Okay, so that would be pH 0. Now, as we go down here, we are decreasing the hydrogen ion concentration by a factor of 10 every time till 10 to the minus 7, and then I got a bit bored, so I've jumped 9, 11, and gone up in 2s there. Okay. But you can see as the H plus concentration goes down, the OH minus concentration here is going up. Okay, and let's have a look at this very important point here, this one. Right, here, the concentrations of H plus and OH minus are the same, they're equal. And look at the pHs there, minus log of 10 to the minus, it's pH 7, which of course we've always known from about year 7. We've said what's neutral, we've said it's pH 7. We'll come back to that. It's not always quite true actually, but we'll come back to that. But anyway, that should make sense. Then as the H plus ion concentration goes very low, and this part of the graph here, the solution, we call them alkaline solutions because the pH is always greater than 7, and the OH minus concentration goes up. Right, just to show you that graphically, so what I've got here is I've done, look at those graphs. So I've done the H plus ions as a red bar and the OH minus as a blue bar. Now, if you look at the scale here, this is the concentration of hydrogen ions in moles per decimeter cubed. And we call this a log scale because look, I've gone up minus 14, 13, 12, 11, 10, 8, 7, 6, 5, 4, 3, 2, 1. So every time, it's called the log scale because every time I go up 1, I'm going up by a factor of 10. If I go up by 2, it's a factor of 100. By 3, it's a factor of 1,000, and so on. But you can see graphically, you can see there when you look at this one, pH 0, you've got high concentration of H plus ions, very low OH minus. pH 4, yeah, they're starting to H plus going down and the OH minus going up. When you get to pH 7, they're equal, and then all these other ones here, the OH column is bigger than the H plus column. So that should give you any aqueous solution you've got, whether it's copper sulfate, orange juice, tea, coffee, whatever. This is always true. Kw, the concentration of H plus times by the concentration of OH minus is always equal to a constant, which is about 1 times 10 to the minus 14. The temperatures, sort of room temperatures. All right, let's just work out. I was talking about pH 7. Let's just get one. Just say this about pH 7 before we finish up. Strictly speaking, you lower down the scale, you've always said what's neutral. Well, it's pH 7. That's not quite true. Okay, that's only true at 298 Kelvin. I'll tell you why in a minute. And when you were lower down the scale, you knew neutral was pH 7, but you didn't know anything that acid solutions were had H plus ions in them. You didn't know that alkaline solutions had OH minus in them, and that's why you couldn't really say anything other than just say it's pH 7. But strict definition of neutral solution is when H plus concentration is equal to OH minus concentration. That's the definition of neutral. So let's work out what the pH is then. So we know that Kw is equal to H plus times OH minus. So let's sub that value into there. So look, let's get rid of the OH. We know that when it's neutral, H plus is equal to OH minus. So in neutral, Kw, and only when it's neutral, is equal to H plus concentration squared. So that means that neutral pH, when it's neutral, sorry, H plus is equal to the square root of Kw is equal to the square root of 1 times 10 to the minus 14, only at 298 Kelvin. So that means H plus concentration is equal to, square root of that is 1 times 10 to the minus 7. We do our pH bit with that. pH is equal to minus log for the hydrogen ion concentration. pH is equal to minus log of 10 to the minus 7, which is equal to 7. Okay, so at 298 Kelvin, neutral pH is pH 7. But what happens to this value here? This actually changes. Kw changes if the temperature changes. So it will be that it actually, we'll see in a later video, Kw actually gets a bit bigger as temperature increases. So that means neutral pH isn't 7 at higher temperatures. It's not quite that. But okay, I think we'll leave that there.